Okay, hello everybody and welcome to the grade 11 class for freemouthhelp.ca. I hope you guys are having a great day so far, and I'm just testing out our microphone right now because in the earlier classes I was trying not to be too obnoxiously loud, but it turned out it wasn't loud enough. So I'm just going to kind of take a look at whether or not it works. Okay, awesome. So it does work. my internet Googling, searching worked out for the best, and God bless people who make YouTube videos on how to fix your live streams. So like I said, hope you guys are having a great day so far, and today we are going to be focusing on trigonometry, which we have been doing for the past couple weeks, but today we are going to focus on the hardest topic, at least from my perspective when I've been tutoring kids, which is the trig identities whole shebang, basically. So realistically today, like I said, we are going to be focusing on trig identities, but when I say trig identities, what I'm really talking about is that we're going to be focusing on understanding the tricks and the strategies that we can use to solve these identities without pulling our hair out every single time. And I know that this is an area that not a lot of people are enjoying, I guess, when they're learning math, but I hope that these strategies can really help you guys, because I know that they've helped students that I've taught in the past, and they help me as well, because when I've tutored in the past, sometimes kids will bring you these really, really crazy identities and you're just like, what even is happening here? But when you apply these identities, it actually really, when you apply these strategies, it really does help. And so I think that today's going to be a fun lesson for those of you who maybe haven't enjoyed this topic in the past. So as always, you are more than welcome to leave questions in the chat. They don't necessarily have to do with the stuff that we're talking about today. The reason that we don't, not that we don't, but basically the thing is that we have kids watching from all over Ontario, and even though, our company, Scholarly Elite Tutoring, is based in Simcoe County and the GTA, we might have students from other areas who are not following the exact same breakdown of units that your school is following right now. So what we're trying to do is just give lessons in a general sense so that everyone can really benefit for before exam time. Although I don't know whether you guys are going to go back to school. I don't foresee you guys going back to school this semester, but nonetheless, you are going to need to know these things. And this is one of those topics that tends to permeate into grade 12 as well. It's a big part of the grade 12 unit. So yeah, basically, before we get officially started, what I do need to do is just add a couple things here. Give me 1 second. Okay. So just going to add these here. Okay. So in grade 11, there are a couple trigonometric identity rules that you really need to have a great understanding of. So I'm just going to get rid of that. And one of these rules really is just specific to the Pythagorean identity. So I'm going to make these a little bit bigger because I realized last week when I was watching back the feed, I noticed that the words were really small on here, and that's hard for me to tell because I'm on my own computer, obviously, and you guys are watching on YouTube. So we're going to try to make this a little bit easier for you to see. Okay, so let us get started. So basically, to give you guys an overview, when we're talking about identities, what we're really saying is we want you to be able to prove that one side of an equation is equal to another based on the rules that you see here on the left. So the primary identity that we really care about, let me just get my correct pen. We really care about this identity. This is the main one that you're going to be using, and I highly recommend you memorize it. It's going to make your life a lot easier. And what's really important to remember as well is that just like with all of math, this is something that can be algebraically changed. And so when we take a look at something here, if we want to isolate for sine squared of theta, instead of having it be written as sine squared theta plus cos squared theta equals 1, we're going to isolate for sine squared theta just by moving things over algebraically. So we leave sine squared theta by itself, and this becomes 1 minus cos squared theta. And the reason I bring this up is because I want you guys to be able to recognize this in a heartbeat. This is going to save you so much time when you are working on these kind of problems. So what the other thing that you can do is you can also isolate for cos squared theta. And then you get 1 minus sine squared theta. Okay. This trio, this guy, and this guy are going to be a big part of your grade 11 identities. And it's really, really important that you're able to recognize how easily these can be shifted. So what we're going to start off with today is just understanding some of the basics and kind of going from there. So what we're going to start off with, before we actually do identities where they equal each other, we are going to actually learn how to simplify identities, because that's kind of the basis for all of what the rest of this unit is. So say I had sine of theta times 1 plus cotangent of theta, and my teacher might ask me to simplify that. And this is a very common thing you'll see on a test. So you've been asked to simplify this problem. Well, we'll call it A. So in this scenario where I've been asked to simplify this, I realistically need to kind of look at it at first and determine, how can I reduce this or make this into something that makes more sense? Well, automatically, whenever I have a more complex identity, so for this particular question, we have cotangent of theta, which is over here. You can see that cotangent of theta equals cosine of theta over sine of theta, because it's the inverse of tan, which is obviously the flipped of that. So I'm going to change cotangent of theta in this scenario. So I'm going to go sine of theta times 1 plus cosine, oh, this is squared, my bad, sorry. So cosine of theta over sine of theta squared. So last week I was doing identities with the grade 12s, and their identities are quite a bit more complicated than these, but the same basic principles do apply in these scenarios. So for example, and one thing that I want to teach you guys in general is kind of the rule that I use to understand these a little bit better whenever I'm confused, or whenever I was confused in the past. I wasn't aware as a teenager when I was first learning these that we can actually just make this a little bit simpler for ourselves by saying, okay, we're going to call sine x, for example, and cos y. And this is kind of the same thing as saying, like, I could rewrite this and say x times 1 plus y over x squared. And in this scenario, it's a lot easier for my brain to look at this, because a lot of times your brain is going to see more complex stuff like this. And I know from experience, when you see really complex things like this and your teacher's asking you to simplify them, sometimes our brains are just like, nah, girl, not going to happen today. This is ridiculous. I'm shutting it down. And that's why a lot of people find these confusing, is because there are so many letters and it looks crazy, but nobody ever teaches us that it just follows the same rules that we've always known about factoring and exponents and all of that fun stuff. So in this scenario, if we remember our power rule from exponent laws, this is going to be multiplied in. So now this becomes 1 plus y squared over x squared. And if we recall, we're supposed to, deal with the brackets first if possible. In this case, there's nothing in the brackets that we can do necessarily. So what we are going to do is actually multiply in this term. So this is now going to become x plus y squared x over x squared. And I'm going to show you what that means on this side. So let's take a look here. We've got, so actually no, let me do this step first. So sine of theta times 1 plus cos theta sine squared theta. So that's what I mean by I multiply this in just like I would with an exponent law, like I did over here. Okay? Now, let's go ahead and continue our work in this field, I guess we'll call it. So I'm going to multiply sine squared theta into both sides. So sine theta, sine of theta, times 1 is sine of theta, and then plus this, which as we know from this step over here, this is just going to be cos squared theta sine theta over sine squared theta. So as you can see, this little method that I use is a very, very simple way of identifying what you are and aren't allowed to do. Because just because we have all of this, all these crazy letters and all this extra stuff doesn't mean that the standard rules of factoring, exponent laws, all of that stuff don't apply. Don't let the letters confuse you. They're just unknown variables. That's really all they are. And if we treat them as such, it makes these a lot easier. Okay, so I'm going to erase this so we have a little bit more space. But again, if you guys have questions about what I'm talking about, you're more than welcome to leave them in the comments and I can address them right away. Or if you want me to cover something else that you're struggling on in your distance learning, I'm happy to do that as well. We can focus on whatever you guys need. That's kind of the whole point of this, is for us to work on material that, works for you. So let's take a look here at what else we can do. Well, now we're at a kind of crossroads, because obviously, we have sine of theta plus this whole jumble, but in actuality, we have to figure something out that allows us to actually add these two together. So what that means is we're going to have to create a common denominator. And the denominator here is sine squared theta, so I need to multiply the left side, or this part, by sine squared theta, which is going to make it into sine cubed theta. But we're actually going to show this step, because showing these dumb little steps is how you get all the extra marks as per the Ontario curriculum. So cos squared theta, sine of theta. So this side obviously stays the same, and in a second you'll see that we will consolidate everything under one umbrella here. So this becomes sine cubed theta, because just like if this was, if sine is x, for example, if we have x times x squared, well, that's going to be x cubed. Same concept, okay, guys? And then that's all under the umbrella of sine squared theta, and this stuff stays the same, plus cos squared theta sine of theta. So now, whenever I get a situation such as this one, my first instinct, because remember, we're just simplifying. We're not trying to make this equal to anything else. If I'm simplifying, I want to get everything as factored as humanly possible, because if we look back to previous years when we learned about factoring, that's really the way that we are supposed to go about things, is factor and reduce the fractions as much as possible. So in this scenario, I have the opportunity to actually take both something out of sine cubed theta and out of cos squared theta sine theta. And that is sine. So again, for those who might be a little bit confused, if we're saying that sine is x and cos is y, in our simplification, this has now become x cubed plus y squared times x, because this is one thing together. And that's all over x squared. So how would we reduce this in this scenario? Well, I would just remove x. I would factor out x by dividing it off of both of these. So I'm going to be left with x, and then in the brackets I'll have x squared plus y squared, and then here I have this, and then this is going to help me reduce, okay? So if you're following along, I'll give you like an extra second to just copy that down, and then we're going to keep on trucking. So here we go. So now back to my blue pen, because that's how we're doing this part. I'm going to use the same concept on this part, and I should be using these equal signs. Gosh, guys, you guys got to call me out on my problems here. Goodness, don't be afraid to yell at me in the chat, because clearly I forget things here and there. So let's factor out sine. So I've got sine of theta, and we have in the brackets, we're left with sine squared theta, just like here. Look, guys, it's the same thing. Just like this, we've got sine squared theta here, and then plus cos squared theta over sine squared theta. And if this particular step confuses you, I highly recommend just working on your factoring skills. I know that it doesn't always come in handy necessarily, but it is something that really is important to understand, okay? So I highly, highly recommend that as someone who has tutored every single math course in the high school curriculum, and I've worked with, I don't even know, probably hundreds of kids over the years. It's really something that is important. Okay, guys? Okay, so now we've got two things that we need to deal with. First and foremost, let's take a look at this right here. This little identity, this guy, sine squared theta plus cos squared theta. Remember how I said earlier we really, really need to be aware of that and be able to recognize it on a dime? Well, looky here. What is this guy? Sine squared theta plus cos squared theta equals 1. Well, if I'm simplifying, I sure as heck would rather have the number 1 there instead of all of that mumbo jumbo. So let's go ahead and change that. So this part stays exactly the same for now. And this part changes to 1 right there. And then we've got this. Okay, so again, I'm going to pull out my orange here so I can show you guys the trick and how this applies to just normal exponent laws, normal rules, nothing fancy. Okay, so don't let the fact that it says sine or cosine confuse you, because this is the same thing as saying x to the power of 1, because sine here is to the power of 1 technically, over x to the power of 2. Well, what do we do? What's our quotient rule? Well, that would be x minus 1 minus 2, which becomes x to the negative 1, which becomes 1 over x. Well, the same dang rule applies here, okay? So this now becomes, I'll show you guys step by step, sine to the power of 1 over sine to the power of 2 becomes sine 1 minus 2 theta becomes sine to the negative, and you don't need to show all these steps. I'm just showing you guys this for your, like, to help you understand what's happening. And this is this. And then this identity is not the final answer, because we can further not reduce this, but simplify this by changing it to cosecant, because we know that cosecant is just the inverse of sine. So this is our final answer, cosecant x. And if you look back at the original question, it was something insane, like all of this mumbo jumbo. This right here. This right here. So we reduced this basically through all of these pretty crazy steps. But the whole reason we're doing this is so that we can understand how to use these steps a little better. Okay, guys? So I'm going to leave that last part there for a second, just so that whoever's copying down can write it, and then we'll move on to another example. And we'll do an example that's a little bit easier. This one I started out with this one because I wanted you guys to get the gist of what I'm trying to explain. We're going to do an easier one just for, you know, the sake of getting it a little bit more, and then we'll go back to a complicated one again, and then we will do some identities. And like I said, if you have questions, feel free to leave them in the chat. Even if they have nothing to do with what I'm teaching, I'm happy to help. Okay, guys? Okay. Alrighty, guys. So let's move on to another example. So again, we're going to do a simplification one, because I think that these are the best way to learn these tricks and these strategies before actually having to complicate things. So we've got 1 minus sine squared theta over sine squared theta. So if you recall what I was saying earlier, nope, not that. I'm trying to get to this. If we look at this Pythagorean identity, and I'm not going to pull it in because it just, what's CSC? Oh, I'm sorry, Allison. So CSC, and let me pull these up actually, make this a little bit easier. Give me 1 second. I will actually be able to show you. So CSC is a reciprocal identity, and I'm just going to bring it onto the screen, Allison, so that you can see what I'm talking about. That's a really good question. Okay. Okay, guys. So yeah, that's actually a very good question that Allison just asked, and I actually will address that before we do this. So like I said earlier, we've got lots of identities that you guys are going to need to know in grade 11 and grade 12. Some of the primary ones that are the most important are these. So I'll also pull up the Pythagorean. So this set here, this I would say is kind of the key to understanding grade 11 trigonometry when it comes to the identities. So CSC is cosecant, which is a inverse function of the sine function. So cosecant, this is another way of saying this, sine to the -1 of theta, which we know that when something is to the -1 to the power of -1, we actually have it in the inverse. So that's all it is. I hope that makes sense. I'm sorry I didn't explain that earlier. I didn't mean to breeze by that. I apologize about that. But all of these here, these are reciprocals. They're all reciprocal identities. So secant is the reciprocal of cos, so it's 1 over cos. Cosecant is the reciprocal of sine, and cotangent is the reciprocal of tan. Okay, so I'll leave these up here. It actually does make things a little bit easier. I'm just going to erase a couple things so that we have some space, and because they're not really parts that we need to worry about in grade 11. So these here are basically our most important identities. And like I was saying earlier, in case anyone just came, and in case anyone missed the very beginning, this identity can be rearranged to isolate for sine squared theta or for cos squared theta. So it would look like this: 1 minus cos squared theta, and this one is cos squared theta equals 1 minus sine squared theta. So my biggest suggestion for when we are doing identities is to really just remember that these can be rearranged, and most of the time the best thing that we can do with identities is to break them down as much as possible. So actually, I'm glad you asked that question, because it does help us roll into this next little area that we're going to focus on. So in this simplification, so say our teacher asked us to simplify the following, it would look something like 1 minus sine squared theta. And this is the easier one I was just mentioning, sine squared theta. Okay, so remember how I said, it's super important, like this guy, this Pythagorean identity is your #1 guy. Like he needs to be the top of your memory at all times, because it's super easy when you have it just at the top of your memory, and you can look at something like this that says 1 minus sine squared theta and automatically say to yourself, hey, that's the rearranged version of the Pythagorean identity, and that's actually equal to cos squared theta. Just like that. So basically in this scenario, we can actually just change this whole top part, the numerator, we're going to change it to cos squared theta. And the bottom part stays the same. And one identity that I'm missing here, where did it go, is this one. And we know that tan, hopefully you guys can see that, tan, I'll just move everything up actually, make it a little bit better. Where is it? So right here we can see that tan of theta is equal to sine of theta over cos of theta, and the cotangent of theta is equal to cos of theta over sine of theta. Well, logically, and I'm going to use another pen color here just to kind of illustrate what I'm talking about. So logically, if, let's say for example, I'm trying to think of something like not totally insane. If we say that, for example, oh my gosh, I cannot think of a single thing right now. What am I trying to say? Let's say, for example, speed is equal to distance over time. Then it would logically make sense for speed squared to be equal to distance over time squared. And another way to write that would be distance squared over time squared. Because again, of that product rule, that still applies, just like we learned in grade 9. So, using this weird example that I just gave over here, I hope that makes sense for you guys. I'm just using this to illustrate something. So because we know that cotangent of theta equals cos of theta over sine of theta, it would make logical sense for cosine squared theta over sine squared theta to be equal to cotangent squared theta. So I hope that makes sense for you guys. And if you have any questions, feel free to drop them in the chat. I really have enjoyed teaching the grade 11 class because you guys always ask really, really good questions. And sometimes things that I don't realize I haven't mentioned. So I appreciate you guys bringing them up because sometimes, because I've done math, you know, I've tutored math for many, many years. Sometimes I skip over things without realizing them. And I think teachers do this too, and we don't mean to necessarily. And I know that in class it can be really daunting to like put your hand up and ask the teacher to go back. But honestly, I think all educators appreciate when you guys interject and kind of ask questions, because it helps us notice what might be missing from our lesson. So anyways, yeah, this kind of smiley face, I thought he looked like a half star. Anyways, not the point. Hopefully this makes sense for you guys. We're going to do another example of a simplification, and then we're going to go over to doing some identities. So hopefully that makes sense. We'll just erase. I'm trying to be a little bit slower because I know last week in the class somebody mentioned I was going too fast, and that is great feedback, and I hope that I'm not going too fast for you guys today. So yeah, okay. Let's pull up our next identity. Let's use purple because I'm feeling fancy like that. So let's do one more simplification, and we are actually going to do we might do two. I'm going to see if I can illustrate my point with just this one, but if I can't, then we will do two. So let's simplify this problem. We have cos of theta times cosecant of theta over tan of theta. So one thing that I find teachers don't usually show that actually really has helped my students in the past is just remembering this idea that fractions really are divisions and that they can be broken down. But before we do that, what I want to show you is how we're going to break this down kind of on a molecular level. So if this is cos of theta, that stays the same because there's no way to really break that down any further. But cosecant of theta, as we can see over here, CSC, is actually equal to 1 over sine of theta. Okay, so that's our numerator. And pretty much my number one tip for you guys is that when you see reciprocal identities in your identity problems, most of the time it's going to behoove you, aka you're going to want to break them down into their more complex versions. So like if you see CSC of theta, you're going to want to break it down so that it says this part, 1 over sine of theta. Because oftentimes, and actually I would say most of the time, the real trick to getting identities as simple as possible is to put them in terms of sine and cos exclusively and just do a bunch of crossing out. Because honestly, these just are normal exponent law type questions, just with a little bit of a crazier premise, okay? So using that same logic of breaking things down into sine and cos as much as possible, we're going to take a look at tan in the denominator and say to ourselves, well, another way of saying tan is sine of theta over cos of theta. So I'm going to use that identity. And now what I'm going to do in my next step, using my equal signs here, in my next step, what I'm going to do is actually just break this down. So in the same way that, like, you know, again, if I had, like, for example, 2 times 1 over 3 over, let's say, 4 over 5, I could actually break that down into 2 over 3 divided by 4 over 5, and then I would break that down even further by doing it as a multiplication where I flip the second fraction, and then I just get this, and I can reduce, whoa, what am I talking about? Yeah, 5 over 6. Okay, so I'm just gonna erase that. I don't know why I'm just scratching it. Goodness. Okay, guys, so using that same logic, we're going to follow those rules just like we would if we were dividing fractions, because that's what this is. So obviously, technically, whenever we have something like cos, even if it was just a number, it's technically over the number 1. So this becomes cos of theta over sine of theta. This is the numerator. This is this part, the top part, okay? And then the bottom part, we'll put a smiley face, is going to be here. We're going to divide sine of theta over cos of theta. Okay? And then essentially, this division, just like we were looking at earlier, is going to become a multiplication, and these are going to flip, just like normal fractions. That's just a fraction division rule. Sine of theta. And just like with fraction multiplication, which is what this is, numerators times numerators, denominators times denominators, and we get cos squared of theta over sine squared of theta. And if we look over here at our quotient identities, we now can see that this is just the squared version of cotangent of theta. So actually we got cotangent of theta twice, but point of this story is really just to kind of be able to do this. And again, if we kind of go through these steps, remember that they're not as difficult as they look if we break them down from the beginning as much as we can, and then just use simple rules. Follow exponent rules. Follow your fraction laws, basically. You can break these down no problem every time. So the way that I tutor, or the way that I have tutored this, I don't tutor myself anymore. We have an awesome team of tutors that we work with. But the way that I've tutored this in the past is less about showing you guys just, oh, here's a bunch of examples and figure it out on your own. I really want you guys to understand the strategies and the logic behind how to do these, because you're going to get, there are millions of versions of Pythagorean identities, and the real trick is to know the roots of how to get to the answer. Okay, guys, so I hope that that's helpful. We're going to keep trucking on forward. I'm going to erase this if that's okay with you guys, and show you the next example. Okay, we are going to do one more simplification because I'm looking at one that's a little bit, that shows kind of a different skill set, and I think it's important for us to understand that. But first, what we're going to do is actually just move these over a bit to give us some space. And we're going to simplify this. So we have cosecant squared of theta minus cotangent squared of theta. One thing I also want to mention, you're going to see all sorts of different versions of the letter that is here. You might see theta, you might see alpha. I've even seen beta on some rare occasions. I'm not a fan of using alpha and beta, to be honest with you. Theta is technically the most correct one to use. Some teachers also use X. I used to use X. I don't know when I switched over to using theta exclusively, but it is the most correct one mathematically, so I think that that's important for us to stick to. Basically, I'm only mentioning this because sometimes people get confused because they're like, oh, well, I originally learned it as theta and now it's X all of a sudden. It means the same thing. All that it means is that this is some angle that we don't know, and you can use any letter realistically to illustrate that. Okay, cool. So, just fixing that there. Awesome. Alrighty, guys. So let's get on the road. We've got cosecant of theta squared, or cosecant squared of theta, and as we know, that is another fancy way of saying 1 over sine squared of theta, and so we will go ahead and do that. Show that part, because like I said, we want to get this in terms of sine and cos pretty much as early as possible. It just makes life a lot easier. So this is squared. And then cotangent of theta is another way of saying 1 over tan squared theta, which actually I'll put this up here for now. And the reason I'm showing it like this is just to illustrate to you in this next step that this is the same thing as saying 1 over sine squared theta minus 1 over tan squared theta. Okay, and again, this is just based on that simple rule that we've learned in grade 9, the power rule, where we multiply this in. Okay, now on to our next step. I'm still not fully expressing this as sine and cos, and the reason is because I have tan here, so I think that that will be our next solution, our next thing that we need to solve. So I'm going to leave this part the same. 1 over sine squared theta is going to chill as he is, and then here I'm going to say minus this. I'm going to break this down, so this is basically a fractional division, so this is going to be written as the numerator, which is 1, divided by, which the division is basically another way of expressing this fraction line there. And I'm going to change tan squared of theta into sine squared theta over cos squared theta. And this is, again, I've just rewritten this instead of having it written this way because it just makes it convoluted, right? That's what this is, this part. I've just broken it down a little bit easier, and this is another tip that I highly recommend, is using this version of breaking things down, because it just gives you an easier visual, and you'll see what I mean when we do more complex problems. So let's go ahead and do this work inside the brackets, because obviously following BEDMAS is still super important, even in grade 11. So here this is 1 times cos squared theta over sine squared theta, and that just becomes, pretend I'm going 1 down, I know that this little thing here cuts off the bottom part sometimes, so this is just the answer, the next step basically. Sine squared theta minus, so basically remember that this is a fraction, so 1 over 1 technically, so this just becomes cos squared theta over sine squared theta. Okay, and obviously it's negative because of this negative here. Okay, so one of the great things about this problem in particular is that we now have a common denominator, which is pretty sweet and helpful, because that means that we can put this all under one umbrella. So in our common denominator situation, we've got 1 minus cos squared of theta, and this common denominator is sine squared of theta. And if we recall from our Pythagorean identity over here, this guy, we know that cos squared of theta is equal to, 1 minus cos squared of theta, not this one, 1 minus cos squared of theta is equal to sine squared theta. So I'm just going to replace this with sine squared theta, which again is like 90% of what identities are, is just replacing stuff. And we know that anything divided by itself is equal to 1. So this answer is 1, because sine squared theta divided by sine squared theta is equal to 1. And that is that's literally as humanly possible, as simple as humanly possible for this problem. Alrighty guys, so I hope that makes sense for you. I personally, I used to hate doing these in high school because I just was so confused by what was allowed and what wasn't allowed. And in my experience since then of years of tutoring, that's typically what students found confusing was, you know, oh, well, am I allowed to multiply this? Am I allowed to, you know, switch this? Remember, it's just based on simple math rules. And if you get confused, you can actually just change everything to X and Y's and simplify that as much as possible until you can apply it back. Okay, so I'm just going to leave that there for about 5 seconds so that everyone can copy it down if they want to. And we are going to spend the next 20 minutes doing some actual trigonometric identities, which is what most of this unit ends up being about. But the reason I taught this first is because solving identities is actually just about simplifying them. And a lot of times I find that teachers just jump right to, and not all teachers, some teachers are awesome, but a lot of teachers that I have seen notes from jump right to identity, you know, equalization, and it doesn't make sense if you've never learned how to simplify them. So hopefully this is helpful for you guys, and I know that you will see this again in grade 12 if you are going to take the MHF4U course. So I hope that you can still apply these rules next year. Okay, guys? Alrighty, so let's do a real trigonometric identity and try out some of these skills we just learned. Okay. So again, I just want to reiterate, keeping in mind all of these key identities. And some teachers actually have you guys memorize them, some don't. I think that memorizing this isn't too crazy. But I know that some of these can be a little bit harder to memorize. What I recommend in general for memorization, this is a real, like, you know, Harvard University memorization hack, is when you have to memorize something, like, for example, say your teacher wanted you to memorize all of these identities, right? Instead of memorizing every single one, what I would recommend is, for example, memorize that secant of theta is 1 over cos of theta, and then memorize, you don't need to memorize that the other one is the opposite because you kind of instinctually know that. Same thing for tan. Don't memorize both tan and cotangent, just memorize tan and then know that cotangent is the opposite. Okay? I know probably for a lot of people you're like, obviously, Arlinda, but honestly, it's something that didn't hit me until university, and I was like, wait, why haven't I been doing this all of these years? Like, I could have saved myself so much memorization. Okay, guys, so let's do this problem. 1 minus tan squared of x. I'll use theta just to be consistent. And then we've got cotangent squared theta minus 1 equals tan squared of theta. Okay, guys, so basically when we're solving identities, this is what happens most of the time, is that you have a left side. This is our left side of the identity, left side. This is our right side. And some teachers recommend starting with the side that looks simpler, that looks more complex. And that usually works. I just don't want you guys to believe that, like, that's the truth for everything. It's not a ubiquitous thing. Like, sometimes it's actually where you have to break down both sides. In this case, I don't foresee us having to break down both sides, but either way, it is important to understand it. Actually, I'm just going to see here. This might be too complex of an example for you guys to just start with. I don't want to freak you guys out. Let's do something slightly easier, and then we'll move over to this, just because I don't want people to be discouraged by the difficulty if they're just starting, if this is the first time they've been exposed to this. So let's try something somewhat similar. We've got 1 over cos squared theta over... No, you know what? We did something like this. Sorry, guys. I had these mapped out, and I don't know how they got jumbled. Okay, here's one that is a little bit easier than the first one that I wrote down, but still actually requires quite a bit of factoring. And the reason why it's important to practice these factoring ones is because they're usually the most difficult. Okay, So this is another one where we are going to use the notion of x and y. So I'm going to put this in a different color, our x and y. So I'm going to call sine y, just because technically sine is y. And I'm going to call cos x. Okay, guys. So another way that we can write this, before I start breaking it down even more, is that technically this is 1 over cosine theta minus 2 sine theta. Okay. And one thing that we should do whenever we have a problem like this, and again, this is kind of a strategy that will help you with most of these problems, is that when you have something like this and you don't have a common denominator, usually the answer has to get to the answer, you have to get a common denominator. So in this case, what we're going to do is I'm going to make a common denominator on this side. Obviously, it has to be cos of theta. So this is going to become 1 over cos of theta minus 2 sine of theta times cos of theta over cos of theta. Okay, why did that happen just now? So we're fully ignoring this right side right now. Pretend that this right side doesn't exist. We're going to deal with this later, this part. We're going to deal with this later, okay? Right now, we're just focusing on the left side, and that's kind of the trick to these, is to work on one side by itself first and then deal with the other side. So just in case anyone is confused by what just happened, what this is the same thing as saying, this is the same thing as saying 1 over x minus 2y. Well, we want them to have a common denominator, so in the next step, I'm going to multiply this side by x on the top and the bottom. And then that's going to give us 1 minus 2yx over x. Okay? That's all that's happening. It's not as crazy. Like, these look a lot crazier than they actually are, and when you start to implement these strategies, it makes life so much easier. So let's actually put this all under one denominator. Gotta put my thetas in there. And cos of theta. Okay. So this is what we've got on the left side. I'm going to leave this as it is right now. Left side, chillin', dunzo, for now. Put my equal signs in, because I'm a savage like that. Great. What's going on over here? Well, if we recall from just our factoring unit in grade 10, whenever we have something squared like this, we cannot just multiply in this squared, because that's not how it works. We have to square this whole concept, this whole thing. So we go sine of theta minus cos of theta times sine of theta minus cos of theta, all over cos of theta. So we now need to use our FOIL to get this correct, to get the correct answer is what I'm trying to say. And again, for anyone who might be using my other strategy, which is very helpful for more complex problems like this, this is like saying y minus x times y minus x. And we know that it's over x. So how do we get to that next step? Well, it's y squared, because y times y is y squared. Then we have negative yx. And in the same way that, you can, using the commutative property in math, which is the same thing, like basically it's saying that 2 times 3 times 1 is the same thing as saying 3 times 2 times, did I say the right order? 3 times 2 times 1 is 1 times 2 times 3. That's what I'm trying to say. You can switch these around. So even though x is first, it's actually going to make more sense for you to say minus yx, because you'll see why in a second. And then we have negative x times negative x, which is going to be positive x. And this is all over x. Cool. So let's follow that same logic and do the same thing with our sines. And again, I know for some people you're like, okay, Arlinda, we get it. But honestly, I remember being just so confused, and I want to make sure that everyone understands. So if you do get it, that's awesome, and I appreciate you guys being patient. But I hope this is really helpful for people who might not have as much experience with this. So hopefully it's a good thing for you guys. So here, sine theta times sine theta is sine squared theta. Then sine theta times negative cos theta is going to be sine theta cos theta. Then here we have negative cos theta times sine theta. And again, like I said, you can rearrange these because it means the same thing. And it's actually easier for you to understand later when we're going to bring everything together. And then we have negative cos theta times negative cos theta, which is positive cos squared of theta, all over cos theta. So this is where the limitations of my method come into play, because obviously with the X and Y method, you can't actually see what the identities are. So that's why we always come back to actually doing the work on the real letter, with the real letters. Because now I can see, well, obviously if I want to get everything in terms of one thing, and in this case, the likelihood is that I want to get it in terms of cos because I have more cos in this problem, I'm going to take this sine squared theta, and using this identity, this guy right here, I am going to change that into 1 minus cos squared of theta. And here I'm going to leave everything else the same, except this now is the same thing as saying 2 sine theta cos theta. Because again, if these were x, y's, then you can just collect like terms. So 2 sine theta cos theta, which is a good thing because as we can see over here, that's something I want to have to make this whole identity equal. And then just adding that last piece here, the cos squared of theta. Okay. And keeping the form with the denominator. Alrighty guys, so let's get to the end of this question. So what is happening here? Well, I know that negative cos squared theta and positive cos squared theta are going to cancel each other out. So those guys gots to go. They are done. And what am I left with? Well, I have 1. So he's chilling. He stayed. He survived. He's on the island. And then I have negative 2 sine of theta and cos of theta, all over cos of theta. And lo and behold, my left side is now equal to my right side. Okay? So I'm going to leave that up for a second and just kind of reiterate some of the main strategies that we use to solve this. So first and foremost, as we can see on the left side, we simplified, and we always want to change everything to terms that we can recognize and cut down as much as possible. So in this case, it's sine and cosine. Realistically, those are going to be your simplest terms pretty much always. And whenever I have to add or subtract something that is in fraction form and not a common denominator, I'm going to create a common denominator. That's another strategy. And that's also why breaking everything down into sine and cos makes more sense, because changing it, you couldn't have done anything if it was still in the secant form. And then if we look at the right side, we use our X and Y strategy to basically make this a little bit easier and to ensure that our factoring, our foiling is correct. And that's really important as well. And then basically we just broke everything down. And also, before I forget, we just are the number one fan of the Pythagorean identity, and we know it inside and out. And like I said, if you don't memorize anything else, memorize the fact that sine squared theta plus cos squared theta equals 1. It will make your life so much easier. I cannot express how. Even in grade 12, that's knowing that and just being cognizant of that is going to help you so much. So that actually is, in order for us to do another example, it would take too long. But if you guys have any questions, you're welcome to leave them in the chat. And yeah. But other than that, I hope that this was really helpful for you guys. And basically, because we didn't get to do many complex ones, we will do a little bit of this next week. Probably next week will likely be our last trig lesson, unless people have trig questions that they want to submit. Just because we've covered pretty much everything in the trig unit, and that's the trig unit by itself, not the trig graphing unit. That's a whole other unit, which we will move on to. But in the actual trig identity and trigonometry unit in general, this is pretty much everything. Okay, guys? So I hope that everyone has a wonderful week, and I hope that you're all staying safe and that you're doing well. In the meantime, if you are taking math right now and you have questions that you don't understand from your distance learning, please feel free to email them to us, admin@scholarlyelite.com. And the team and I will take a look, and we will address them next week during the chat. But I thank you guys for being here and for listening and your questions. And I hope that you guys that are in grade 11 have a wonderful afternoon. And we will talk next week, same time, same place. And I'm going to drink some water before my grade 12 class because I have been talking nonstop all day, and that's probably not very good. Okay, thank you guys. Have an awesome week. Okay, so hi everyone. If you are here for the grade 12 class, I want to say welcome and thank you for joining us. We are going to get started in just a minute. And if you do have any questions that you'd like us to address, please feel free to leave them in the chat. I'm happy to do my best to answer the questions, although some of you guys go to schools where your teachers have some really cool and intense questions, and I know that sometimes I don't know, just hopefully I can address them, but that's what we're here for. And so you are welcome to leave them in the chat and I will do my best to explain them for you. But if we don't get any questions, today's live stream is actually going to focus on equivalent trigonometric expressions, and we're also going to talk about related angle formulas. So just some really fun, cool stuff, and explaining what the heck is going on in these topics. So yeah, but first, what we're going to do is teach the equivalent trigonometric expressions. And I rewatched last week's lesson, and I know that I know now that the words were really small on the actual equation sheet, basically. So if you ever find that I'm writing too small or that the equation sheet that I've put up is not large enough for you to actually read the letters, please let me know in the chat. It's hard for me to gauge because I'm looking at my own computer screen and I can't tell based on like what you guys are seeing on YouTube necessarily. So yeah, but today we're going to mitigate that by keeping these quite large, and hopefully that way you guys can see everything and we can explain everything for you. So I'm just going to start out by drawing like a unit circle. Not a unit circle, no, yeah, kind of a unit circle, I guess we could say. Actually, why did I do that backwards? I should draw the circle first. So let's swap it up here. Do a circle. Like a lot of fresh fruit around. You know what I mean. Chocolate chips in my pancakes. Stuff like that. Okay, guys. So we got this. That wasn't super central. I'm going to try to make it as centered as possible. Bear with me, you guys. Okay, so today we're going to be discussing equivalent trigonometric, wow, clearly I've been talking for like 5 hours straight today. We're going to be talking about equivalent trigonometric expressions and how we get them and why they exist. So in order to do that, I'm just going to pull up a different couleur here. Let's use purple. Some Lakers colors. Nobody come at me for that. Okay, so by grade 12, we are going to be talking about trigonometry quite a bit. We will have spoken about trigonometry quite a bit. Wow, sorry, clearly, again, like I said, my brain is just starting to go. But at this point, your teachers typically expect you guys to know all of your basic main points. So obviously when we learned the unit circle last year, we knew that this is 0, this is 90, this is 180, and got 270. And for a lot of people, they kind of get stuck with these and they just have a really hard time converting them. But it's super important that you guys remember the main ones. So 90 is equal to pi by 2. 180 is equal to pi. This is 3 pi by 2. And this is 2 pi. Okay, you guys? So, now, in discussing this, and the reason I'm mentioning this is so that we can specifically remember that 90 degrees is 2 pi. Pi by 2, sorry. Now, if we take an angle in the first quadrant, so let's say arbitrarily, this is like 45 degrees, which another way of saying 45 degrees is pi by 4. Sorry, I'm trying to write so that you guys can also see. So this angle here, we're going to call it pi by 4. has its terminal arm sticking up over here in the middle of the quadrant. And we know that if we were to say basically, what is this point here, that can be expressed as cos and sine. Okay, now, in order for us to get the quadrant, in the quadrant, into quadrant 2, with the terminal arm giving us pretty much the exact same angle in the sense that like it's going to be exactly a mirror image. I'm going to try my best to do that. Something like that, basically. We need to add something. So if this was 45 and then here, this was technically like all the way around, it would have been 135. We know that, so from here to here was 45. Well, then logically from here to here is also 45, or pi by 4. Okay? And in order to get from here at 0 to here, your angle is 0. And you're adding pi by 4, pi by 4, pi by 4. Another way of saying that is saying your angle, whatever this theta is, which is pi by 4, plus pi by 2. And if we look at this in terms of degrees, it's actually going to make a lot more sense, because if we say 45 degrees plus 90 degrees is 135, well, that gives us this whole angle. Okay? And one way of looking at this is if this is AB, well, then this is negative BA. How does that make sense in terms of our equivalent trigonometric expressions? Well, if again, this is cos and this is sine, and sine is B, so we'll look at, for example, sine of theta right here, or we can say sine of pi, sorry, not sine of pi, sine of theta plus pi by 2 equals cos of the original theta. So, for example, sine, and I'm going to do it in degrees because I find that people find that easier, and then we're going to do it in radians. So sine of 45 plus 90 is equal to the cos of 45. Well, let's look at our standard triangle that we've been talking about these past couple weeks. Wow, my lines. Just getting crazy. Crazy with these insane lines that we're doing. Let's do this. So this is a 90, 45, 45 triangle. Another way of saying that is a 90, is a pi by 2, pi by 4, pi by 4 triangle. And I know that my hypotenuse is root 2, and this is 1 and this is 1. So what is the cos of 45? Well, the cos of 45 degrees is the adjacent over the hypotenuse. So that's going to be 1 over root 2, which we're going to rationalize to be 2, to be root 2. Well, the sine of 45 degrees plus 90 degrees is also root 2. Okay, you guys? And that makes sense because sine is positive in quadrant 2. Okay. Let us try this with the same exact thing, but instead of degrees, we're showing radians. So this is this identity right here. Equals cos of pi by 2. Of pi by 4, sorry. And it's the same concept. Because basically, that is just how we can break this down. If we take a look here, the cos, so we have the adjacent, opposite, it's all going to be the same. Okay, so that's really what's happening here. Let's just pull up another Exemple. Okay. Basically, the main ones that we really need to know are this one. And some schools actually make people memorize these, which I think is so difficult, but I mean, it's doable. It's just a lot to memorize on top of all the other stuff you need to know. And this one. These are kind of the three standard ones that you'll see. Okay. These are the equivalent trigonometric ratios, and they do come in handy quite a bit. So, oh my gosh, so many calls today during this free math help for some reason. Like, obviously, we are busy, and you should call back later. Okay, guys. So let's use this on some real exemple, because that's where this gets more difficult, is when you're given crazy questions to do, and hopefully this can be helpful. So we're going to leave up this formula sheet here, just so that everybody can kind of refer to that as I'm talking. I'm going to change my couleur. Okay, so your teacher will often give out questions like, what is the equivalent trigonometric expression to sine pi by 12? So using our trigonometric equivalencies here, basically, we know that sine of theta, if we look at this one, and remember, we can just flip these, obviously, right? So if we know that sine of theta is equal to cos pi by 2 minus theta, well, that's very important information for us, because we can just go right ahead and plug this in like this. So sine of pi by 12 is equal to cos of pi by 2 minus pi by 12. And this is just your standard equivalent, like making a common denominator situation. So this is going to become cos of 6 pi by 12 minus pi by 12. And just going to move it up one more. And then this is going to become cos of 5 pi by 12. And these are actually equivalent. This will give you the exact same answer. Okay? So hopefully that makes sense for you guys. We are going to do something a little bit different, where we actually flip the idea around. So I'm just gonna, I'll give you guys about 10 seconds to write that down, and if you have any questions, feel free to leave them in the chat. And we'll do something relating to this, but a little bit different in a second. Alrighty, guys. So let us do another problem here that's somewhat like a reverse of what we just learned. So let's say cos of x is equal to 0.109. Then what is the value of sine pi by 2 minus y? Well, before we answer this, and actually let me put a question mark there because that's going to bother me. Before we answer this, let's kind of look at what we're looking at in terms of the equations. So we've got cos of x, which if we look here, this one here, which is equal to sine pi by 2 minus y. Well, given that that is our equivalent expression, then we know that sine of pi by 2 minus y, pi by 2 minus y, is equal to 0.109. Simple as that. Okay, guys, so that's kind of just to illustrate the point of what we're talking about here. Let me just erase. Hopefully that makes sense for you guys. Alrighty, guys. So this is where things get a little bit crazy. So if cos of 11 pi over 180 equals 0.9816, what is sine of 79 pi over 180? So what we need to do is we can express the angle of 79 pi over 180 in a different way. And we can express it as pi by 2 minus 11 pi, over 180. So therefore, we're just going to go ahead and we get sine of pi by 2 minus 11 pi over 180, and that's equal to cos of 11 pi over 180. And so let's think about how we're going to get to this. So 180, so this has to become literally sine of 180 pi, 90 pi is what I meant to say. My bad. Minus 180 over 180, I mean minus this, which is really another way of saying sine of 79 pi over 180 is equal to cos of 11 pi over 180, and we know that that is equal to 0.9816. Alrighty, guys, so hopefully that's helpful for you. And that's really, again, like most of the time these types of questions just involve you kind of determining what would be the common denominator, how can we express this in a different way, and making it a little bit easier in that sense. Okay, so what we're going to move on to, unless you guys have any questions about this, are our related angle things, which we touched on a little bit last week, but today we're going to talk a little bit more about correlated angles. Okay. But actually, I'm just gonna start a new page here and just bring this bad boy in and do this. Where did my related angles go? Oh, there they are. Okay. So equivalent obviously means that the answer is literally the same. Related is a little bit different. We're also going to talk about correlated. So last week we talked about related angles, and really that's just angles that you know, are going to give you that same expression, basically, the same trigonometric answer in the end. Now, what we're going to want to do, usually with related acute angles, sorry, I'm really tired, you guys. Usually what is going on with the related acute angles is a little bit different. Sorry, just give me 1 second. Let me pull up all the right worksheets here, just so that we're looking at the correct stuff. So, okay, guys. So, let's take a look here. Let's take a look-see. So with our related angle formulas, there's a couple different things that you need to know. First of all, you might get your teacher asking you questions like, you know, sine of pi minus x. Write that in a simpler form. Well, we know based on this identity that the simplest form of writing this is really just sine of x, because x and theta are interchangeable. You might even get, for example, like this one. Let's see here. So for example, you might be asked to find the exact value of like sine of pi plus pi by 6. Well, we know that when we have something like that, we can just take a look here and see what is in the related angle formulas that can help us. So I have this one, sine of pi plus theta, which means that my theta is pi by 6. And that's going to be equal to negative sine of theta, which is negative sine pi by 6. And I know based on my triangles, that pi by 6 is going to be, sine of pi by 6, I mean, is opposite over hypotenuse, so that's going to be pi by 2 because of this. And then this is 1, and this is root 3. So that means it's negative times 1 over 2. And we have got 2. So this makes this negative a half. Okay, you guys? So there's that. Let's try another one. And if you have questions, please feel free to let me know, okay? So let's say that we've got, let me just double check that we're using the right stuff. So find the exact value of cos pi minus pi by 3. And the question asks us to find the exact value. Okay, so we know that when we have pi minus some theta, because this is cos pi minus theta, I can look over here and I can see that I do have an equivalent, a related angle formula. So I have negative cos of pi by 3. And that's because the identity itself is negative cos theta, is equal to negative cos theta. So at this point, I'm just going to go ahead and solve for the cosine of pi by 3, which is, cosine is adjacent over hypotenuse, which is 1 over 2. So then I get negative a half. Technically that's the half, and then multiply in the negative, and you get negative a half. So it's not as crazy as it seems, you guys. And it's important to remember that it's really, really something you can just break down So sometimes your teachers will give you guys stuff like, let's see here. Let's try cos of 2 pi by 3, and the question asks us to use the relationship, tan, not tan, sorry. Use the relationship cos pi minus theta equals negative cos theta to evaluate. So if this is cos 2 pi minus 3, and they're asking us to evaluate in this format, well, then what we're going to have to do is cos of pi minus 2 pi by 3 is equal to negative cos 2 pi by 3. And if we're thinking about what is a related angle, well, I could just kind of sit and think about, well, what is my cos of pi by 3? And cos of pi by 3 is 1 over 2. Okay, and then so I'm just going to let you guys copy that down for a second. If you have any questions, let me know. Okay, so now what we're going to say here is that we know that this can be solved in this way. Well, negative cos 2 pi by 3 is going to be negative. And if I'm going to just go ahead and do pi minus 2 pi by 3, that's technically 3 pi over 3. And we know that 1 pi by 3 has a cos of pi by 3 is equal to negative cos 2 pi by 3. And we know that this is 1/2. So the answer is negative 1/2. Okay, you guys? So hopefully that makes sense. I'm going to leave that for a second. Alrighty. Now, I know that this isn't the most exciting unit in math. I know that a lot of people don't like this unit. That's kind of why we're trying to go through it, just so that we can get it over with and not have to worry about it. So if we think about related angles, we know that we're looking for the angle that can tell us, you know, that similar expression that can give us the information that we need. When we talk about correlated angles, and we're looking at this, and then this is a 90-degree triangle, and we know that this is, let's say it's some angle x here, and this, because we know that our rule of triangles is that a plus b equals c, these 2 points, so this needs to be pi by 2, because this is pi by 2, because it's a 90 degrees, equals pi by 2. Then this needs to be pi by 2 minus x. So for example, cos of x equals sine 90 minus x, because these are equivalent. Okay, so let's go ahead and do some correlated angle work. And then it'll probably, unless anybody has any questions, it'll probably be an easy wrap up. So, be a quick wrap up today. So let's talk about the correlated angle and what it all means. Okay, so let's do that. Just going to erase this bad boy really quickly. So let's say that I asked you for the correlated angle for tan of 120, and I'm using degrees just because it helps illustrate this a lot easier for people who find radians difficult to understand. So with 120 degrees, if I'm looking at my unit circle, pretend that that's not as terrible as it looks. Goodness gracious. So we've got this. Wow, that's even worse somehow. Anyways, it doesn't affect what we're trying to say. It's just going to be there. X, Y. So if our unit circle, if we're thinking about it like this, we know that 120 degrees is about 60 less exactly than 180, so it should be over here somewhere. And this is 60 degrees, and this is 120. So we know that 120 degrees is in Q2, and this acute angle right here, this one, is 60 degrees. And basically what we're going to do is we're going to say, well, the tan of 120 is equal to the negative cotangent of 90 minus 60. And that makes sense. Where is it here? So the negative cotangent of 90 minus 60. So basically you're looking at the opposite side of the right triangle. And it's going to be the inverse of that. So this is the correlated angle, but if we're looking at the related angle, then the related angle would be tan of pi by 3. Because 60 degrees is your related angle, because in Q1, that's the acute angle that you would use as a comparison. Okay, guys, so now let's talk about this in terms of radians, sorry. So we have here, oops, sorry, not in terms of radians, but basically what's going on, sorry, I didn't mean to confuse you guys. So this here, the related angle, is going to be negative tan 60, which is root 3. And we know that based on our triangle. So we've got 60, 30, 2, root 3, 1. So tan of 60 is the opposite over the adjacent, so root 3 over 1. And in this case, we've got that there. Alrighty, guys. And we know that in this thing, in the quadrant 2, it's going to have to be negative because one of them is going to be negative. Alrighty, guys. And so this is root 3. So basically when you're asked to solve for a correlated angle, it's actually easiest to go ahead, solve for your related angle just to make sure that you're correct, and then make sure that your sign is correct. Okay? So let's go ahead and do something else. Not something else, the same concept, but just with radians at this point. Alrighty, guys. So, just gonna make sure we're getting the right thing here. Alrighty, guys. So let's say we were given the question tan of negative 8 pi over 3. And they want us to find the correlated acute angle. So now, first what I like to do is picture this on the unit circle. Wow, my lines are just terrible today. I don't know what's going on with me. There we go. Alrighty. So whenever we have something like this, obviously we know that from here to here is 1 pi, and from here to here is another pi, which makes 2 pi all the way around the circle. So if this is over 3, then that means that from here to here is 3 pi out of 3, which is technically 1 pi. And then all the way around the circle is 6 pi out of 3, which is technically 2 pi. And then that means we did another pi by 3, another pi by 3. So pi by 3 is 60 degrees. So that means we had 1 here and 1 here, which means we're right about here. Alrighty. And that puts us... Actually, no, sorry, we're supposed to be going the other way around. So if this was positive 8 pi by 3, that's where it would be. But actually, because we're technically supposed to be going negative, I'll show you what's going to happen. Alrighty. So we're actually going in the negative direction, which means we need to go 2 pi, which means negative 6 pi over 3. Oh my gosh, I did it wrong again. I keep going in the wrong... It's such a habit to go the normal way that your brain just automatically does it. Wow. Those lines though. Classy. Okay, so we're actually going this way. So 6 pi, 1, 2. So we're in this quadrant. Okay. So this is negative 8 pi by 3. And technically this here, this distance, is pi by 3. Like it's equivalent to that. Now, the related angle is positive tan pi by 3, because in this part we know that tan is positive, and in this part we know that tan is positive. So in Q1 tan is positive, and in Q3 tan is positive. So that's why it's related. And we try to always use the Q1 angle as our related acute angle. Okay, now we know that tan, oh, I wrote that weird. Alrighty. Tan of pi by 3. Well, I know that again, and super important that you guys memorize these standard triangles because they will help you out a lot, like a lot. So we have pi by 3, and this part is pi by 6, 2, 1, root 3. So we know that tan of pi by 3 is opposite over adjacent, so that is going to be this over this, which is root 3. Well, that actually is also going to apply up here. So we have cotangent pi by 2, pi by 3. And actually, let's see if they're... I don't have them in my thing here. Let's just see if there's any standard. Yeah, so the correlated identities do exist. And it just depends on which quadrant you're in. So if you're in basically if you are in Q2, Q2 or Q1, you can just do that minus alpha. So it's obviously going to be the inverse, which is why we have the cotangent. And we're going to make this into cotangent of pi by 6, which again is pi by 3. So this is technically the final answer right there, but this helps you understand what it is. Alrighty guys, we're going to do like one more example and then we're going to wrap up for the day. But if anyone has any questions, you're more than welcome to drop them in the chat and I'm happy to answer them. So basically I just want you guys to understand that correlated angles are the inverse of related angles, meaning like that's why we switched from tangent to cotangent. You would usually switch from like sine to cosecant, things like that. Okay, so for example, if we're being asked what is the correlated acute angle or correlated angle of secant negative 5 pi by 3. So first things first, I'm going to want to take a look at my related angle. It's just easier to think that way because that's kind of how we've always thought of it. So negative 5 by 3. So remember, that would be meaning that we're going clockwise instead of counterclockwise. So that would just end up being here because pi by 3 is 60 and that's 1 less than 2 pi. So that should be there. And that means that whether it's secant, cosecant, or tan, or cotangent, it's going to be positive because it's in the first quadrant. And that means that here, the related angle is tan, which is positive in the first quadrant, of pi by 3, which we know. Oh, sorry, not tan. I didn't mean to write tan. Oh, not what I was trying to do. So secant of pi by 3, which is 2. Because again, using this logic, pi by 6, pi by 3, 2, 1, root 3. And we know that secant, which is 1 over cos, and if cos is 1 over 2, and then secant is 2 over 1. So coming back to our correlated angle, what we're trying to figure out, obviously, is the inverse, or the opposite. So the opposite of this is the cosecant. And that makes it cosecant pi by 2 minus pi by 3. And again, this is because it's in the first quadrant. If it's in a different quadrant, then it changes the rule. So in the second quadrant, in the first quadrant, it's pi by 2 minus a. Here it's pi by 2 plus a. Here it is 3 pi by 2 minus a. And here it's 3 pi by 2 plus a, which makes sense because here you're basically saying 90 minus a. Here you're saying 90 plus a. Here you're saying 270 minus a. And here you're saying 270 plus a. Anyways, so let's just wrap that up there. So we've got, technically this can be broken down into cosecant of pi by 6. And the answer is 2 as well. So these answers are always going to be the same. It's just that you need to understand how you got this answer in order to be able to show that on a test. Okay, guys, so I'll leave that up for a second. If anybody has any questions, feel free to drop them in the chat. And if I don't get any questions in like the next, 30 seconds or so to a minute, then we will probably wrap up for the day. Just because it's a little bit of a quieter crowd today. But again, like if you guys are in grade 12, and actually, you know what? Before we go, I'll try to explain the correlated angle identities quickly again. We can do like one more example. Okay. Alrighty, guys, so let's do one more example. Just because I know that this is a really weird topic and it's quite a lot to grasp. And then, quite frankly, like, unless you're going to be a math major in university, you pretty much never need to know this stuff ever again, which let's just keep that between ourselves. Like, it depends, I don't know. I've taken calculus both in my business degree and in my science degree, and in both of those degrees the calculus does not actually require knowing this stuff, to be honest with you, but that is neither here nor there. Okay, so guys, let's do one more example. So let's say we want the correlated angle of the cosecant of negative 11 pi over 6. So again, let's talk about the related angle first, just because it is a lot easier. So obviously, if we're looking at negative pi by 6, then a full 2 pi would have been 12 pi by 6, or negative 12 pi by 6, which again actually puts us in the first quadrant. It's just a little bit lower because it's at 30 degrees, somewhere here-ish. That's pi by 6. Okay, you guys. So that means that the related angle would be cosecant of pi by 6. So again, it's just easier to do it with like, you know, cosecant of x is equal to 1 over sine of x. So let's get sine of x. Well, sine of x is opposite over hypotenuse, so that would be 1 over 2. And then the cosecant, 1 over a half, and then this would actually just be 2. So our answer here is 2, which means that we know our answer over here is going to have to be 2, but how do we get there is the better question. So remember that this, when we're talking about correlated angles, we're talking about the inverse or the opposite. So if this was cosecant, then here we're going to talk about secant, and this is going to be pi by 2 minus pi by 6. And we're going to get secant of pi by 3. And that's not too difficult to get because secant is just 1 over cos. And so cos of pi by 3 is 1 over 2. And then the secant is 2 over 1. Okay, you guys, I hope that made sense for you. Again, I'm going to leave that there for a minute. And just one thing I want to reiterate, because all of the examples we did were in the first quadrant, we used the pi by 2 minus a formula. So that this one here, pi by 2 minus a being the related angle. But if you are in another quadrant, these are the rules. You have to change it. So in the second quadrant, it's pi by 2 plus a. In the third quadrant, it's 3 pi by 2 minus a. And in the fourth quadrant, it's 3 pi by 2 plus a. And the way that you determine what quadrant you're in is obviously by actually like sitting and figuring out, you know, if you're in a negative 11 pi by 6, that means you're technically in the first quadrant because you have to go almost to 2 pi and then minus 1 pi by 6. And we know that the related angle, aka the angle that's exactly the same with the same terminal arm, just in the first quadrant, is pi by 6. So hopefully that makes sense for you guys. If it doesn't, feel free to leave a comment in the chat, and I'm happy to answer it. But if nobody has any questions, and again, like if you have questions that don't have to do with the lesson, I'm happy to answer them. Just email them to admin@scholarlyelite.com, because I know with the grade 12 questions, they're a little bit harder to type in the chat because you have pi and stuff. So if you want to just like send our team like a PDF of the question that you're wondering about, then we can definitely address that during next week's free math help. Okay, guys? But in the meantime, I wish you guys an awesome week ahead. I hope you're staying safe. I hope you're doing well. One thing that we have been mentioning to all of our students at scholarlyelite.com is that we understand that this is a crazy time right now. And if you are going through stuff that you want to talk to an adult about, or just like really just a person, there's lots of help. We really recommend Kids Help Phone. We're not affiliated with them, but they're an amazing organization. You can just Google Kids Help Phone or go to kidshelpphone.ca, and there's lots of ways that you can get in touch. They have calls that you can do. You can text them. You can message, like chat with them. They have awesome counselors that work there, and we know that right now is really scary and really insane in terms of what's going on in the world. So if you need someone to talk to, that's available, and it's something that we highly recommend. So don't feel like there's no one out there. There are people that are willing to talk and willing to help, and you're not alone. Okay, guys? So I hope that you have a wonderful week, and we'll see you guys back here, same time, same place, and I wish you all the best. Okay, everyone? Have an awesome day. I'm just going to leave this up for like 30 more seconds, and then we're going to shut down the stream. Okay? Thank you, guys. Have a good one.